Hello YouTube viewers, welcome to my show Future Friday. In today's episode we're gonna continue our moon series and we're gonna figure out moon power. So let's dive right into it. Now first a quick overview about power. Basically in space you cannot just go say hey, hello, how are you? You cannot communicate like this. You have to have power for communication. You have to have power for radio, you have to have power for walkie-talkie. Basically we need to have power for communication, otherwise we simply can't talk. We're gonna need water. Basically if you are familiar with the International Space Station, you must be familiar with the fact that it recycles upwards of 98% of water. Now many of you would wonder why the heck it's so high when on Earth you can barely get a 50 to 60% recycling efficiency. The reason is in a space station it's airtight. Basically a lot of water that we consume basically from sources, it's not going out by urine, it's most of them is going out by sweat, and you are breathing, so water vapor is coming out of your nose, so that water is not capturable easily. Actually, I mean, like you have to make an airtight building, and in case of International Space Station it is airtight. That is why we can recycle that high level of efficiency. Basically we can recycle 98% of water. Now in case of moon it will be the same because it still has to be airtight, so we can expect very high efficiency, upwards of 90 to 99% water recycling efficiency. And when we're talking about Mars, same technology will apply. But recycling water of course consumes a lot of power, so we have to have a lot of power for that. Then we could talk about food. Now International Space Station does not have a refrigerator as of now, so these people they do not know ice cream. Now of course for one mission that was ice cream was sent, but more often than not they never can eat. Now because space constraint they did not put a refrigerator there, but if you are expecting an industry to build around the moon, you have to have good amenities for people to live in there. And I'm not talking about scientists, I'm talking about construction workers or engineers or things of that nature, not just guinea pigs that you sent up there for studying the low gravity effect of low gravity on human body. I'm talking about people who gonna do work there, not be a guinea pig, just the people who work there. So you have to have refrigerator, you have to have water heater, because we generally send food in what we classify as dehydrated system. Benefit, it's a very small, very energy efficient, and basically it reduces the weight while keeping the nutrition content, so it's a very good in that regard. However, you have to have a lot of energy to rehydrate it, so that is also needed. And in terms of air, now this is critical aspect. Even if let's say you take a very large volume of air, let's say 800 cubic meter or 1000 cubic meter, it has, if your mixture is perfect, like basically like Earth's atmosphere, you have more than enough oxygen for a very long time. However, you don't have enough CO2 removal. Basically we humans excrete CO2. Now we are very sensitive to CO2 level, and when I mean sensitive, I simply mean we're gonna die if CO2 concentration goes up. So what is that concentration? Basically anything above 6 to 8%, you will start to feel a bit dizzy. Now when I say dizzy, you're not gonna act like a drunk, you simply will be low energy mode, you won't even know it. People outside who are observing, they can figure it out, oh you are in low energy. Now if it reaches 11 to 13%, you dead. That's it, there is no discussion about it. That's why International Space Station has lot of fans, air circulation fan, backup fans, then some extra backup on that. The reason for that is when you are in 0G environment, the air that you are exhaling is pooling up there, so basically you can suffocate in your own breath. Now of course it does not happen because you have put motion into your air by excreting them out, but to make sure that does not happen when you're sleeping or you're breathing very slowly and you have, basically you're getting suffocated by a CO2 blanket, they have air pumps. So we have to have that even in moon, because even though moon has gravity, it's not strong enough for air currents to work normal level. So we have to have air pumps and CO2 sensors and CO2 scrubbers. All those things require power. So long story short, if you have power, you are alive. You know power equals death. Now one thing you don't have to worry about is basically freezing to death. You will not freeze to death in space. Basically if International Space Station ever loses power, the people inside them, if you remove any other constraint, basically let's say radiation or water supply and all that, they're gonna die off from heat exhaustion, because anything we built in space, we generally put a lot of insulation in them, and best quality insulation out there. And on top of that, there is vacuum outside it, which is the greatest insulation we can build. So if I translate that, basically let's say you have a moon habitat that has 1000 cubic meter of volume in it, and you have people in them. Every person that is in there is acting like a heating rod of 100 watt capacity. Basically I'm standing here, I'm giving off 100 watt of heating element. Now if I'm exercising, I'm giving off upwards of 500 watt. Now that must be taken outside. Now in case of Earth, atmosphere takes care of that. Now in case of moon, there won't be atmosphere because it's a sealed environment, so that heat will seep out. Now it will seep out very slowly. That is why International Space Station has giant radiator. The size of the radiator on basically International Space is bigger than a trolley truck, 18-wheeler. It's bigger than that. So you have to have that. Now, if that radiator breaks, that heat will be trapped, and you're gonna suffocate, basically die from heat exhaustion. Now, of course, the temperature won't reach very high. Basically, you won't reach a point where it's like 900 degrees Celsius or things of that nature. But our body will become difficult and difficult. Like basically 40 degrees Celsius, 50 degrees Celsius is achievable, and you don't want to be there. You're gonna die of heat exhaustion. So life in space is directly proportional to power. You have power, you are alive. You don't have power, you dead. So first, we have to address some issues that we are talking about. First, we need a lot of it. Now, if you think about humans in terms of like, okay, I'm going to build a city on Earth, and what kind of power consumption we are talking about, multiply that by 100 times. You need a lot of power in moons, because I told you, like many things we don't take into granted. Basically, water, the fact that you can go to the bathroom and flush happens because you only need one water pump to put the water on top and then let the gravity do the rest. In moon, you will not have that luxury. You have to have water pump both ways. And in terms of air, basically air conditioners and fans, you have to have them. It won't be a luxury, you have to have them. Otherwise, people can be like suffocated to death in one area. Basically, if you have one coordinate and fan stopped working there, people will suffocate to death there only. Even though there will be more than enough oxygen, but CO2 will pool up. So we have to have a lot of power, and it has to be 24/7, because you cannot be like, okay, we are gonna sleep, so we have lower requirement. You still have every single requirement. Basically, to keep us alive, you need 24/7 power, and the downtime would be very dangerous. Downtime in this sort of scenario would be lethal. So these are the issue. We need a lot of power, we need 24/7, and we need basically no downtime. If we have to have downtime, it has to be scheduled. Basically, this is at this time for 1 hour our power plant will go offline. We will figure everything out, and then at that time, only for that long, we can handle it. So these are the core issues with power. So first thing, everybody will think about, hey, solar. Now, solar works very well in space simply because there is no atmosphere. So you will get the exact power rated to your solar panel, and you will get it constantly. And because moon rotates so slowly, you will get 15 days of 24/7 into 15 continuous power. No problem with that, as long as it's in solar tracker. Because if you put the solar panel and that's like that, because moon is rotating, the angle will change and you will not get high efficiency power. So you have to have solar tracker, and if you don't, you have to compensate for that. Basically, you have to put a lot more. So if you did that, let's say you have solar tracker and you put a lot of solar panel, you're gonna get a lot of energy. No issue with that. However, the consequence will come at the fact that after 15 days of awesome power, you will have no power. So because it will not work on starlight. Starlight is not basically bright enough. There is not enough luminance in them to basically drive these things. So, and that is why we simply don't rely on them at further than Mars. Even at Mars, these are not very useful. That's why Curiosity rover has RTG. So that's the first part with the solar. The only way you can make solar work on moon is simply go back to my last video, and like that's why we have to have 3 solar farms 120 degree apart. So we have to use RTG, basically radioisotopic thermoelectric generator, RTG. Now, if I have to simplify RTG, think of it, it's just a battery, and it's a very long lasting battery, and it's simply, there is no moving part in this, so it does not break. And we have actual real life experience with these puppies. Voyager probe have been going on for upwards of 20 years. 20 years, let that sink in. There is a battery that is in space that has been continuously working for 20 years. And it's doing that. It's like it's still going. It will still work for more than 5 to 10 years still from today on. So it is very simple, and it does work. There is no, and one of them is still on lunar surface, because Apollo program was also carrying few of them. Now, many of them RTGs are generally not only used for electricity, they are also used for thermal performance. Basically, if you have a rover, basically like a, when you're talking about a Curiosity rover, the context of that is like if you have batteries, or if you have basically processor, they have a lower temperature limit. You cannot be like, okay, let's cool it to liquid nitrogen degree. Now, of course, that's cool for overclocking, because you are putting so much energy in the system. You are overvolting it and providing too much power. So for a core level, it's not free, suffering any consequence. But when you're talking about something that is in space, freezing to death is a very serious probability. Like, I mean seriously, like satellites can simply stop working because they don't have like if you cool them down too much, they can freeze simply because they do not have the over voltage or a lot of power. And batteries really don't like low temperature. If basically you have lithium ion battery, nickel cadmium battery, whatever have you, if you have low temperature, these batteries are like, yep, I'm out. And many sensors require a certain temperature to work properly. Basically your temperature probe must need a reference temperature to be like, okay, this is hot or this is cold, otherwise it will simply tell you the difference. So we rely on these, and these are tested. Like this is as tested as you can make it. Consequence, they have very low power. Basically the RTG that is used in Curiosity, they barely gives off 1 kilowatt of power, barely. So generally what they do is like the RTG, the rover will be standing at night, it will charge the battery during the night using the RTG, and during the day RTG plus the battery power will allow it to drive. And because it's a daytime, they can easily see everything and they can move around properly. But once they deplete the battery, RTG can no longer direct drive it. So RTG can maintain the communication, but it cannot direct drive it. So this is the limitation of RTG. Now, when we are talking about moon mission, we're gonna have RTG because this is the only technology that we can rely on continuously for 10 years. So basically, let's say for air circulation and water reclamation or things of that nature, basically something that we have to have, we're gonna rely on RTG as a backup system. Basically, we will have enough RTG that in case, let's say, solar farm breaks down or anything else breaks down, the RTG will take care of us in long term. Basically, at any given moment, let's say for first 5 years you had no issue, but let's say on the 6th year solar farm breakdown, no problem, RTG will at least keep you alive. That is why we're always gonna have RTG wherever we're gonna have humans, because this is very reliable. Consequence, neither Elon Musk nor Jeff Bezos can touch it. Basically, it has a way too many red tapes because you have to put plutonium into them, and even uranium designs do agree, and there are some upgrades. Now we will find out whether these upgrades are good or not, because Curiosity rover, the basically RTG in Curiosity rover is a different design. So RTG generally break down not because the half-life of the basically radioactive material is gone, it generally breaks down because the thermoelectric couple that is there, basically the thing that is converting heat, basically temperature gradient into electricity, that breaks down. So by changing the composition of the radiation itself, we can extend the life. So that is being used in basically Curiosity. We will find out how long does it run and live long. So RTG we will have RTG for absolute safeties. Then we come to, okay, if we're gonna have RTG, why not put nuclear reactor? Now when I'm talking about nuclear reactor, we have to talk about KiloPower nuclear reactor from NASA. Now NASA flat out, once they realized they have to go to Mars or they have to go to moon for long term, flat out they knew there is no other option than nuclear. Now in the simplified sense, when I'm talking about nuclear power, you have to understand nuclear power has a really bad luck. So think of it this way, when Manhattan Project was over, like okay, they figured out a bomb, they figured out how to blow each other up, the scientists, the engineers, the technicians, they are all like, okay, let's do something productive with this technology. They sat down, they figured out a reactor, they built a test reactor in MIT or somewhere else, and then they like moved forward with that. But here's the problem, the design was never kept refining constantly. Basically, once the design was approved, they built a approved design from the government body, they just ran with it. General Electric generally ran with it. Every company that could get their hand on the blueprints of the nuclear reactor, they just ran with it. They never refined it. Basically, to give you a context of that, every nuclear reactor that is running today is running on the design from 1970. To give you a context of that, if I give you a car engine from 1970 versus a car engine of 2020, you will not be able to tell them like, is this even made by the same species? That's how far apart they are in terms of technology. When it comes to nuclear reactor, they are literally, nobody ever pushed it to like, it works, they ran with it. Nobody like pushed it further, to refine it further, to make it safer. So that created an inherent flaw in many of the reactors, because when Chernobyl blew up, after the engineering detail and a lot of analysis was done, the first question was how the heck it survived this long. Like there was so many cost cutting measures. One of the measures was very painful and horrifying, that caused a lot of radiation caused illness, because when you have a nuclear reactor, you put Geiger counter everywhere. So Geiger counter comes in ranges. You have, if you're dealing with nuclear reactor, you're gonna have a Geiger counter that is very sensitive, simply because it can detect minor leaks. So we'll have one that. Then you will have another one that can detect major leaks. Now they bypass the major leak ones because they did not put it there. So the thinking of that time was like the radiation is at 3. Now 3 is safe level, but here's the deal, the meter can only go up to the 3. So even if it was 12, they would not have any way of noticing it. So that amount of cost cutting was done. So yes, fault happened, humans do make mistakes, things happen, but designers are supposed to design it such a way as a quote unquote fail safe. it was not there. So that's why Chernobyl happened. Then we come to Fukushima, because after Chernobyl everybody was like, yeah, that's only happened in Russia, that only happens in like that stupid design. Now that was true, but then again human stupidity came into the context. So let's talk about Fukushima. Now Fukushima is pinnacle of human stupidity or Japanese ego. Basically, in every nuclear reactor that is operated by civilian, not about military but civilian operation, generally they have a committee that comes there and regulates it and monitors everything, and they share their knowledge. Basically, from India to Japan to everybody who has nuclear power plant have this committee going around, making check, because sometimes you need to look from far to figure out what's going on. So they look up nuclear power plant. They're like, everything is awesome, but you have two core flaws. Flaw number one, your sea wall is not high enough. Basically, if tsunami happens, your wall will not stop it. Option number two, basically the biggest stupidity you did, you have a lot of backup generator. Basically, if they had one backup generator, they're good, but they had 12 of them. So you will think that's awesome, but yes, all of them was in the same place. All of them were under sea level. Basically, all of them was at what we call basement. So earthquake happened, tsunami happens, water crosses the basically inadequate seawall, and because every backup generator was in basement, it gets flooded, so they cannot start the generator because of the earthquake. Safety systems were triggered and reactor was cut down. You have to go to basically backup power. Backup power was not triggered, and boom. So you can understand human stupidity. Like, this is written from nuclear test committees, like, dude, basically increase the height of your seawall, do not put all the freaking backup generator in the same place, and please don't put them in the basement. But the response from Japanese team was like, we've been doing this for 40 years, we know what we are doing. And boom. On top of that, here's the hilarious part about nuclear reactors. Water in them generally explodes. Nuclear reactor itself cannot explode because the uranium or whatever nuclear fuel is used is generally diluted. It has to be diluted. Otherwise, the moment you turn on the reactor, it will go kaboom. So nuclear power plant cannot go nuclear bomb. Basically, no matter what you do, you cannot set a nuclear power plant into a nuclear bomb. You cannot do that, because the moment you try to do that, it will explode. You won't be like, okay, I'm gonna put it on, I'm gonna start it on, then some bad thing happens, and then no, it's not a James Bond reality. The fuel rod that are used generally is dilute. They have to be dilute. Otherwise, the moment they will insert into the reactor, it will blow up. So the problem with using water is that water has what we call thermal properties. Now, on top of that, there is one property. If you have high enough PSI, little bit of catalyst, if the temperature is high enough, it will split. Basically, you will have thermolysis, invert of basically electrolysis. Instead of using electricity, you're gonna get basically thermal energy to break the bonds apart. Now, what happened in Fukushima and Chernobyl is basically water split apart. In case of Chernobyl, the water split apart because there was a catalyst used in the control rods. So when water splits apart, the problem is you have rocket fuel there. You have really hot hydrogen, you have really hot oxygen, boom. So water explodes in nuclear power plant. So whenever you see something going boom and breaking things apart, that's always water, not anything else. Nuclear power plant cannot go boom. I have no idea why the heck Hollywood loves it so much, but nuclear power plant cannot go boom. So, but water can. Stay away from water. If water is at 500 psi and scorching hot at 600 degrees Celsius, yeah, it's very close to thermolysis, and little bit of catalyst equals rocket fuel. So that did happen. So when NASA started to work on this, and this is a very old project, this has been working on the background for a very long time, they threw everything out. Basically, we're not gonna build the nuclear reactor based on something. We're gonna start fresh. So every aspect of this has been thoroughly tested and double tested and double checked. The moment somebody pointed out, yeah, water is not good, they threw out water. So what they're relying on is sodium. Basically, they're gonna have a nuclear reactor core. That core is gonna heat the sodium. Why sodium? Sodium has much more stable temperature. Basically, if you want to heat water to, let's say, 500 or 600 degrees Celsius, how we do in nuclear power plant and core power plant, you have to pressurize the water. Basically, you have to increase the PSI of the water. Consequence, that PSI means your pipes, the pipe, basically outer diameter of the pipe will become very large. Basically, your thickness of the wall will go from this to this. Basically, that's how thick you have to make sure your pipe is, because water is uncompressible. In sodium, you don't have to worry about it, because sodium can absorb upwards of 700 degrees Celsius without going any boom. So they use sodium. So heat pipe is working on sodium, and that heat, once it goes on top, basically here, it is run by a Stirling engine. Benefit of Stirling engine is completely enclosed. Side effect, it's not that efficient compared to a very high pressure steam, but since you don't have the luxury of infinite water supply in space, that was out of the question. But this has the advantage: if you can put it, let's say, on the dark side of the moon, or place where there is a constant shadow, and it can dump the heat properly, because I told you, space, even though cold, it's literally a very good insulator. So if you can figure out a radiator that can dump that heat, it's gonna work phenomenally, because the only core principle of a Stirling engine is basically delta of between the temperature, between the hot side and cold side. So hot side in this puppy can go upwards of 700 degrees Celsius, which, if you think about it, for a nuclear reactor, that's very cold, because they designed it in such a way that no matter what happens, it will not go kaboom or quote unquote melt down. So they built it in such a way that hot side will be only 700 degrees Celsius, cold side will be as cold as they can make it, and they will get power out of it. So their early test was done, like, this is a real design. This was really tested with actual uranium and actual all that. It was tested and it worked phenomenally well, and they've simulated all sort of fault. Basically, they disabled the heat pipe, they disabled all that, and it's designed from day one in such a way that it will not fail catastrophically. No matter what happens, it's not gonna go boom. So it's done. Now benefit, NASA find out it's very optimistic. Basically, they will have 3 designs, basically 1 kilowatt design, a 5 kilowatt design, and 10 kilowatt design, or they might even just figure out making one big one. So 10 kilowatt is the maximum that they're gonna planning for, and it's upwards of 200 kilogram. Yeah, it's a very lightweight reactor. So you have a lot of power, and it is throttleable. That's the biggest problem with RTG. RTG gives you 500 watt, that's it. There is nothing about it, like that's 500 watt, use it or lose it. Here you can control it, so that means you, in low power, you can extend the lifespan. And in terms of lifespan, because everything is solid state other than the thing that is moving in the Stirling engine, it's supposed to work for 10 years constantly with varying power outputs. So this is very amazing, and NASA is flat out betting everything on this. Because if you really want to go to Mars, when you really want to do anything, because on Moon you have a lot of solar power, on Mars you don't, so you have to use this. Mars human mission can only be done by this. But so, consequence of this, if RTG has a red tape, this has a freaking red, very red paint. So because this is a proper full-fledged nuclear reactor, you have to have lot of things to figure out before you get clearance for this. But NASA can get clearance for this, and they are working towards it, and it has been tested. So soon, I think by 2025, first of this reactor will be sent in space for further testing. But as of now, this is very well designed, very well tested, and maybe many of the design lessons learned from this will be used in nuclear power plants of the future, because water goes boom. We don't want going boom. We want things to be like calm, chill. So we may figure out, hey, instead of using water, let's use sodium. Which in 1970 engineers were like, yeah, water is a good starting point, but we have to move to salt reactor. This is a salt reactor. That's the problem with nuclear technology. Basically, people just ran with it without improving it. So the design we have is inherently flawed. So, and when you have ego, boom. So this is 3 options that I have given for my mission. Basically, then we come to critical aspect. In my last episode, I talked in detail about like why we have to have 3 basically landing site, 3 habitat zone. Basically, you have to have each of them apart 120 degree. Benefit, it allows you to evacuate in case of basically asteroid or meteorite crisis, and it also allows you to have continuous solar power. But you have to transfer the power. Basically, you have to transfer it. How do you gonna do it? Now, if you do transfer the power, it also allows you to have smaller batteries. Because in case of a battery, if you have to only take care of basically, let's say 12 hour of power, 12 hour day, 12 hour night, battery won't be very huge. But if you have to make that 12 hour battery to last for, let's say, 15 days, yeah, the battery size will be like few 100,000 tons. Basically the 1 gigawatt scale battery, that would be way too heavy to send to space. So this will allow us to reduce power demand from the battery if we interconnect it, because if we interconnect it properly, we will always have one that is working at 100%, another that is working at 50%. So you'll always have more than enough solar power to utilize properly. So in that scenario, if we interconnect it, you don't have to worry about too much battery, and all the 3 spots will have enough energy. But then the question becomes, okay, it's much easier to make solar farms, and we have been doing this, like Apollo missions have that. We know how to do that. How are we going to transfer it? Now, there are 2 ways, of course, wired and wireless. Now, when we are talking about wired, we simply cannot rely on AC system. We have to do what we classify HVDC. You can check my detailed video about it here. Basically, HVDC has some benefits, and one of them is like you can send the cable very far. It does not have attenuation. Basically, if you have AC and you take one cable and stretch it to, let's say, 10,000 kilometers, it will not have any signal at 10,000 kilometers. You will simply not receive any electricity. But in HVDC, you can stretch it out as far as you can. Of course, the resistance of the cable will waste some energy, but you can send it if your resistance is low enough. So in case of moon, and if you are in a polar area, we are talking about distance in like 700 to 900 kilometer, it can be managed. And HVDC only need one conductor. That's the interesting part. In monopole configuration, you only need one conductor. That's it, one. And the reason for this is why we want to use wire is simply because I'm not talking about going to the moon for a luxury purpose or science. I'm going about industry. Industry needs a lot of power, continuous power. For that, we need to have a stable infrastructure. Now again, the consequence of this itself would be like hundreds of tons. Basically, one BFR would be sent just to have cable in it. So maybe doable, may not be. Now, is there any alternate to this? Yes. We can try microwave wireless power transmission. Now this has multiple benefits. This caught my eye simply because if we figure this out, because you can check my detailed video about solar power from space. If we do this today with current technology, I'm not talking about technology that we do not have. I'm talking about the rockets we have today. I'm talking about the solar cells we have today. Everything that we have today, we can take care of entire humanity's power need from space. But we do not know how to transfer wirelessly efficiently. Basically, we can transfer wireless electricity, no problem with that. It's just we do not know how to make it efficient enough. But moon allows us to basically do a very good test run. So let's say we, instead of HVDC, we tried this. It's a very good test ground, and we're gonna have RTGs as a backup. And if we have KiloPower, we may not even have to do that. This will be just as an add-on. So if we figured out any company, let's say Blue Origin went there, and NASA is taking care of everything, and Blue Origin is like, hey, we want to transmit power from landing site A to landing site B. We want to try this. Awesome, try it, because you don't have to worry about hundreds of thousands of regulation when you are beaming up megawatts of microwave. In space, you don't have to worry about it too much, and on moon, there is nothing to worry about. So in those sort of scenario, this provides a very good testing ground, like real world testing ground. And if that can be figured out properly, we can send power from sun, basically power from moon itself to Earth. Now, consequence, you have to have multiple receiving station. Otherwise, you can do it. Like basically, moon can provide enough power with current science. I'm not talking about helium-3. Helium-3 is like beyond me. It's like we don't know how to make fusion reactor, and people want to build a neutronic fusion reactor. Like all I ask of you, just research the ignition temperature of basically deuterium-tritium reaction and reaction for helium-3. Just check the temperature, what is needed to ignite it. 15 million degrees Celsius is just for deuterium and tritium ignition. Try to figure out what is the temperature for helium-3. So anybody who's like, we're gonna mine helium-3, A, there is not enough of it. B, it's a very sparsely basically scattered. So basically you are talking about filtering gold out of seawater. It's literally that much. Heck, you might have more gold in the sea. So it's very hard to get out, and even if you get out, we don't have any reactor that can use it. We don't know how hydrogen fusion, and people want to use helium fusion. It's beyond me. It's like, first let's build a hydrogen reactor, then we'll talk about helium reactors. So that is why interconnection can solve a lot of problems. If we did wireless one, it can take care of entire humanity. So this was my presentation of my imaginary lunar mission about, I hope you liked it, learned from it, or it was entertaining enough for you. In that case, please leave a like, click the ads that are shown in this video, that will directly help me. And if you didn't like, you know what to do, you can dislike it. I would urge you to press this twice to show me your extra disappointment, and leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.